Today we want to continue talking about vector operations. We've talked about vector addition and scalar multiplication. And now we need to talk about dot product and cross product. Probably just dot product today. It's interesting enough. The things that we have to do with these operations are talk about how to do the operation, the mechanics of the operation, and then we also have to talk about the geometric interpretation of what's going on. So we need to do mechanics and geometric interpretation. We mentioned yesterday that the dot product is the scalar product because we're going to take a vector, dot a vector, and come up with a scalar. And the cross product, we're going to take a vector, cross a vector, and get a vector. And for both of these operations, we need to know how to do it. Here are two vectors, find the dot product. Here are two vectors, find the cross product. And we have to know what those quantities tell us, what these products tell us. Any questions before we get started? Let's talk about dot product. Got a couple ways of finding the dot product. One way of finding the dot product is to find the sum of the products of the corresponding components. One way to find the dot product is to calculate the sum of the products of the corresponding components. So let's grab a couple of vectors from R3. It'll work the same in R2, but let's do R3. This will actually work the same in R4 or R5. Note that the two vectors have to come from the same space. Otherwise, we can't operate on them together with a dot product. So we find the sum of the products of the corresponding components. So we multiply the corresponding components. And then add them up. That's the dot product. The sum of the products of the corresponding components. So for example, if U is 2, -1, 3, and V is 0, 4, 1, then U dot V is 2 times 0 plus -1 times 4 plus 3 times 1. So I have 0 minus 4 plus 3, negative 1. Perfectly legitimate question. What does this mean? Possibly legitimate deflection. We'll get to that. Perfectly legitimate response to that deflection. This is one way of calculating the dot product. But wait. It's another way of calculating the dot product. The product of the magnitudes multiplied by the cosine of the angle between the vectors. Magnitude of u times the magnitude of v times the cosine of theta. We should note that this would require us to know the angle between the two vectors. So usually we're going to be using this to find the angle between two vectors, rather than already knowing the angle between two vectors. So usually we'll use this to find the angle between two vectors. So in our example up here, I've got this vector u and this vector v. I can't use this formulation of the dot product to calculate the dot product because I don't know the angle between those two vectors. So most of the time, we're just going to use this to find the angle between two vectors, and that will tell us some stuff. So this tells us that the angle between two vectors will be the cosine inverse of u dot v over the product of their magnitudes. Note that now that we have crossed over into vector operations, when we use the dot, we're talking about the dot product. So the stuff around it has to be a vector. I did not put a dot to indicate the multiplication between the magnitude of u and the magnitude of v, because those are two scalars. Those are just the magnitudes of those vectors. They're just scalars. One thing to note that since we're using finding theta with the cosine inverse, if you imagine two vectors, you could think of two angles between them. The short one and the 360 minus that angle, the long way around. Clearly, we're going to be getting the short one. Because if we do a cosine inverse, that will always be something between 0 and 180. So since cosine inverse will give us 0 and 180, we're getting the shorter angle between the two vectors. So this is going to put out an angle between 0 and 180 degrees, or between 0 and pi radians. We have two vectors. There's two places we could put an angle, the short one or the long way around. Since we're using the cosine inverse, we're going to get the short way around. All the time when I'm doing Calc 3, I bring up that this is mostly just to find the angle between vectors because we usually don't have that to begin with. I only ever draw this picture when I'm also teaching a trig class, which is strange. But there it is. So with this information, if we have the vectors u and v, like in the previous example, we can calculate the magnitude of each of these vectors. I spelled v wrong. So you just use find the magnitude of u and v. So 2, -1, 3, 0, 4, 1. So 16 and 1 is 17. And magnitude of u is 4, 9, 10, 14. So u dot v is -1 divided by the magnitude of u times the magnitude of v. Oops. And I need to calculate the machine. Nope. I can barely do like addition and stuff in my head. So those are the same. This is the arc cosine. Arc cosine is the notation we came up with because we're like, oh, people are going to confuse this with a -1 exponent. And everybody's like, oh, nah, that won't happen. And then it happened. And people are like, oh, well, dang it. 1, 2, 93.7. We had known that before. We could have taken the magnitude of u times the magnitude of v times the cosine of that angle, and that would have given us the dot product. Oops, glare. Uh-huh. We don't have to worry about any x-axis. This is the angle between the two vectors. So this is an angle that's relative to just with the two vectors. This is just based on these two vectors, whichever way they're facing. There's a 93.7 degree angle, whichever way they're facing. So we don't have to worry about any axis.
Professor, can you hear me?
Yes.
Yeah, I was gonna ask, when you were plugging that in, you put a -1 on the top. Why is that?
The -1 is what we calculated as the dot product. So u dot v is -1, and that's our numerator up here.
Okay. Got it.
So it's -1 is our u dot d. Any questions? How's everyone okay? Cool. I'm glad you brought up the x-axis thing because it's relevant to our geometric interpretation of what this dot product is all about. Any questions before we turn the page? Since I just wrote something else on this piece of paper and now it has to dry. See, I'm confident that there's only going to be one more page of notes. But if I turn the page now, then this is going to get all smudged. So partially also because I just have to stop. It can't be all math all the time. So you have to punctuate. We should have a conversation about movies and TV shows because I love having conversations about movies and TV shows. Here's fun opinion. While this is drying, it's already dry by now, but I can't resist this one. So I don't know if you watch the MCU, but it used to be that Netflix was making the television shows in the MCU, like Daredevil. That was really good. I really like Luke Cage. I really like Jessica Jones. I started watching The Punisher, and I had this idea about The Punisher. So the casting, perfect. When they're like, oh, he's going to be the Punisher, I'm like, oh, no, he already is the Punisher. That is like perfect. I never would have thought of that because I'm an idiot, but Jesus, that is perfect. So, perfect. Whoever decided on that casting and approved it should get an award. But anyway, beside the point. I didn't really watch the show, and I thought one thing would have been really awesome for the Punisher because remember, I grew up in the United States in the 80s, and so I was around for a lot of Punisher stuff. And if you've read old Punisher comics, they're kind of trash. Just gun porn. It's just gun porn. If you're into guns, you're going to be into the Punisher, and kind of that's what it was about. And it was really accurate representations, not of like using guns, but their visuals. They were drawn accurately. Beside the point. The way that, because comics have to be reset into the current times, unless you want to do a whole period piece, the Punisher is, as normal, a veteran of whatever the most current war is. And I thought what would be dope for a Punisher series was not him going around shooting people and taking revenge, but him just getting together with a bunch of other veterans and working through their PTSD. It's like no like shooting people or like all this violence, just have like a deep think piece where it examines these kinds of important issues. And I know exactly how the fans would have reacted. They would freak out. And if I was a writer on that, I would never be allowed to write anything comic related ever again. But I think that would have been my shot. They say, Leach, you got a shot. You're writing the Punisher. Do we need a lot of guns? We don't need an ammo budget at all. We don't need the fake guns. I need some psychiatrists, though. I need some veterans to talk about, and we're going to examine PTSD in veterans who come into combat. And that's what the show is going to be about. I guess we would need some flashbacks, but was that? I know they wouldn't because it says Punisher on the top, so you're expecting him to go out and like torture people, right? And what does that say about us? It's like imagine Batman. I don't know who grew up with Batman, but you know what who Batman is known as? Batman is the world's greatest blank. What is it? Detective. How much fucking detecting did he do in any of the Batman movies? That's a big fat none. All he did was fucking beat people up. And I was into it. I mean, it's like, oh, yeah, punch that guy. That guy's a mobster. Yeah, punch that dude. Oh, that's true. He did a couple of things. But look how long it took to get into that. Look how long it took to get into that. Look how many Batman movies we have before someone's like, oh, you know he's supposed to be a detective, right? And like, oh, call the CSI writers. So, anyway. But yeah, you're right. They did have some detective stuff, but I think it should be like the primary thing. Uh-huh. Yeah. Yes. Yeah, that's true. I am kind of forgetting about the Batman because I didn't I didn't really like it, but I like that they did something different than just like I'm gonna beat people up. Yeah. I'm Calculus Man. We need the dot product. Where's the dot product? How he did that. Yes. I really kind of worry about Christian Bale. He's a little bit too into that. He's like, we'll put a fat suit on. He's like, no, 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 no. I'm gonna get fat. Play Dick Cheney. It's like, well, we could just like, oh, no, I'm gonna do it. Yeah. I go, you're enjoying this a little bit too much. All right, what are we talking about? I think if I was Christian Bale's position, I wouldn't like be so method. I think you would like during the shooting of Batman or the filming of Batman. Uh, I think I'd get dressed up in the costume and like go out and patrol the streets and like find a mugger and beat him up. Just because. And then when like I get arrested, they're like, "Oh, what the hell are you doing?" I'm Batman. It's method acting. Break out of prison. Get some underage teenager to break me out of prison. I mean, do we realize how irresponsible Batman is? Come here, teenager. We're gonna go fight crime. Um, in what way am I qualified for this? You do parkour. Come on, let's go. That's true. Yeah, to be fair. All right, Batman. Sorry, Bruce. What are we talking about? All right. Let's think back to trigonometry or physics or engineering statics, all the other places that you've seen vectors before. And let's think back to components. We like to break vectors into horizontal and vertical components. What's going side to side, what's going up and down. It's convenient for us because they're perpendicular, and it's always nice when we have perpendicular coordinates. So we have vector V, and we like to break this vector into two components. I missed the bet. I missed the bet. I could have made this purple and used red and blue. Oh, well, I missed it already. I have to get over it. We can write this vector as the sum of two vectors that are perpendicular. I just realized I'm going to be writing V sub V, and I hate it. We have a vertical component. And we have a horizontal component. Now I'm trying to deal with it now. It's not very easy. Where V is the sum of these two vectors. We like this because we have a bunch of vectors going all the way around. If we could break them into these components, it's really easy to see what's going on in our system. What's going horizontal, what's going vertical, how are they all interacting? And the vector V is the sum of its two components. Its horizontal component and its vertical component. It's the sum of these two components. Because we like everything to be nice and orderly, we have a standard position for the vector where the angle of the vector is measured from the positive x-axis and counterclockwise is the positive direction. So we have this angle theta. So if this vector v makes an angle of theta with the horizontal, what is the magnitude of the horizontal component? The horizontal components, we only need the magnitude part. You said it's the horizontal component. So that's
I already left forward, bro.
So that's telling us the direction.
Oh, it don't matter, just like.
Were you asking a question?
You can't respond now.
Oh yeah, no, exactly. No, you can unmute yourself. It's fine. Type it in the chat if you're asking me a question. I just didn't understand because my hearing is bad. Sorry, what? So the horizontal component, we don't need to write this as a vector. We're going to write it just as the magnitude. But the magnitude of the horizontal component is the magnitude of v times the cosine of the angle theta. Just thinking back to trig, the magnitude of the vertical component would be the cosine of the vector, the magnitude of v times the sine of the angle. We don't need that one right now. We can see that we need this one because we're talking about the dot product. The dot product is two magnitudes and the cosine of the angle between the vectors. So the vector v has this horizontal component, magnitude of v times the cosine of theta. And then it's got this vertical component that we're not really as concerned about. So what this v magnitude of v times the cosine of theta is how much of the vector v is going horizontally. That's what we're getting out of this calculation. This is how much of the vector is horizontal. That's what we're getting out of this magnitude of v times the cosine of theta. If we just look at this term, if we think about this horizontal component, magnitude of v times cosine of theta, that's how much of v is going in the horizontal direction, just thinking in terms of components. What we're calculating with the magnitude of v times the cosine of theta is the dot product of the vector v and the unit vector I. But I is a unit vector with a magnitude of 1. So v dot I is just going to be the magnitude of v times the cosine of the angle V makes with the horizontal. Theta is the angle between V and I. That is the angle that V makes with the horizontal. That's the angle that V makes with the horizontal, the angle between V and I. So what we're doing with the dot product is we're doing this, but in general. When we look at V dot U, we're looking at how much of V is in the direction of U. What is the projection of V onto the vector U? It's the projection of V onto the vector U. It's just, instead of doing a horizontal component, if I've got some vector V, instead of looking at a horizontal component, I'm looking at some other rando vector U. And we're thinking, how much is V projected onto U? Yep. So this is the projection of V onto U. So when we were breaking things into components, we were doing dot products. The dot product is just a generalized form of that. Instead of always having horizontal and the angle between with the vector makes the horizontal, this is the angle between the vector and any other vector. So any other direction. All right, that's it for today. I will see y'all on tomorrow. Everybody have a good day. And thanks for playing.